Hi guys, welcome to the first tutorial for COS100 Introduction to Informatics. Today we're going to be reviewing some of the applied topics from the first and second lectures, focusing on binary numbers. So we're going to practice converting decimal numbers into binary numbers and converting binary numbers into decimal numbers, and we'll also perform some ASCII encoding operations as well. And we'll finish up with a couple of discussion questions, and all of these will help you prepare for your final exam. So to get started, bring up a word processing document. So start up Microsoft Word or OpenOffice Writer, one of the word processing programs, and quickly create a new document and save it as COS100 Tutorial Exercise 1. And we do this because if something goes wrong with your computer or mobile device, the autosave functionality will allow you to recover your document so you won't lose all of your work. So moving in to the background knowledge for our tutorial exercise. So remember in lectures 1 and 2 we looked at the process of representing decimal numbers using binary numbers. So the binary values, how they will appear, how they actually are represented in the memory of the computer. So recall that the decimal number system is a base 10 number system. So we can use symbols from 0 up to 9, so we've got 10 symbols there to actually represent our numbers. And the position of the number indicates its value. So we have our ones column, our tens column, our hundreds column, and our thousands column, and so on. So if we wanted to represent the number 12, for example, we put a 2 in the ones column and a 1 in the tens column, and they add up to 12. Also, before we move on, it might be useful to actually open up your calculator app. So in Windows, the calculator application is found under the Applications menu or under the Start and the Accessories menu under older versions of Windows. So bring up your calculator application. Just as a quick demonstration, there's been a few questions about having powers of 0. So if we have a number to the power 0, anything to the power 0 is always 1. So if we go 2 to the power 0, we get a result of 1. If we go 10 to the power 0, again we get a result of 1. So any number to the power of 0 is always going to be 1. So that's how we get our ones column. So just following on here, a second example, if we want to represent the number 256, we place a 6 in the units column, a 5 in the tens column, and a 2 in the hundreds column. So our binary number system works the same way, only it's a base 2 number system. So it only has two numbers, 0 and 1, instead of going all the way up from 1 to 9. And each of these numbers is simply referred to as a bit or binary digit. So like the decimal system, the position of each digit actually indicates its value. So instead of working in powers of 10, we're going to work in powers of 2. So we have a ones column, a twos column, a fours column, an eights column, all the way up to a 128s column. So we're only using 8-bit integers, 8-bit numbers for our exercises. You can go all the way up and add as many bits as you need to represent the numbers. So the more bits you have, the bigger the number that you can represent. So again, following on with our example, if we wanted to represent the number 12, number 12 is made up of 4 and 8. So we can represent that by placing a 1 in the fours column and a 1 in the eights column. So we've got another example here. If we wanted to convert the other way, if we want to convert the binary value 1001, 1011 into decimal, all we do is create a table like the one you can see down here in the exercise, where we line up each of the individual bits, each of the binary digits, under their column and under their value for that particular column. And then we just figure out which ones have a 1 in them, and then simply add the value of that column up to get the final result. So for example, we can see here we've got a 1 in the ones column, a 1 in the twos column, a 1 in the eights column, and a 1 in the 16s column, and finally a 1 in the 128s column. We simply add all of those values up, for which we have a 1 here, and we get our total of 155. So therefore the binary number 10011011 represents the decimal value 155. So in this approach too, we can also we can convert back down. So for converting a decimal number into a binary number, we simply need to work through and divide our original number by our column values, starting from the left and moving to the right. So in order to convert 12 into a decimal number, we start by dividing it by 128. Now, 128 doesn't go into 12, so we put a 0 here, and there's a remainder of 12 from that division. So we take our remainder and we move it down to the next row, and we divide it by 64, which is the next power in our table up here. And again, there's no 64s in 12, so we put a 0 there, and we have a remainder of 12, and we drop that down. Same with 32, there's no 32s in 12, so we drop our remainder, and we have a remainder of 12, we drop that down to 16. There's no 16s in 12, so we have a remainder of 12, and we drop that down. Now we work on the 8s column. Now, there's actually 1 8 in 12, so 12 divided by 8 equals 1, and we have a remainder of 4. So we drop our remainder down. In the next one, we divide our remainder, which is 4 by 4, and here we have a 1. So there's 1, 4, and 4, so 4 divided by 4 gives us 1. We then have a remainder of 0, and we drop that 1 down through, and we can see that for these final two results, because our remainder is 0, we're going to have a value of 0. So that means that we've actually reversed the process and found our binary representation for the number 12 by dividing through all of our column values. So the second little thing we're going to look at today in the tutorial is actually decoding ASCII characters. So if we're presented with a sequence of bits or a binary number here, we want to decode that and figure out what ASCII character that represents. Now, the first step for this particular process is to convert our binary number into a decimal number, and we simply do that by lining up all of our individual bits underneath their values, and then simply add up the columns that have a 1 in them. So, for example, we have a 1 in the 1s column, 1 in the 4s column, a 1 in the 8s column, and a 1 in the 64s column. We add all of those up to get a result of 77. Now, once we've actually got our decimal value, we can then go to the ASCII table that we've put a link here to, and we can actually go and look that number up under the decimal value here. We can see that it corresponds to the capital M character. So the bit sequence, or binary number 01100001, represents the character, the letter M. So now we have some exercises for you. In the first set of exercises, you'll be converting these binary numbers into decimal, and in the second exercise, you'll be converting these decimal numbers into binary. In the third exercise here, we've given you a series of binary numbers, and we want you to decode them into ASCII encoded characters. So you'll have to use the lookup table to work out what characters those sequences of bits actually represent. To finish up, we've got a set of discussion questions. Now, for these discussion questions, you'll have to review the material from lectures 1 and 2 and construct an answer that's based upon that material and that fulfills the criteria of the question. So in the first one, you've got to look at how color images are represented. In the second question, we want you to identify 2 different types of data that you come in contact with every day. So examples might include emails, account balances, text messages, photographs, and we want you to describe or explain how they might be stored in a digital system. So make sure you go and review particularly the second lecture, have some good tips on how to come up with an answer for that particular question. And then the final one, we've got a little scenario there. So if you've got a desktop computer and a laptop computer, you install the same application on both of them, you notice that there's actually a performance difference between them. You notice that the desktop computer is far more responsive than the laptop computer. Why do you think the desktop computer is faster? So to answer this question, make sure you have a look at lecture number 1 and have a look at some of the differences between laptop and desktop computers. So focus on things such as the processor speed, the memory, and also things like power requirements and constraints that they might have on them to construct your answer. So good luck with today's exercise, and if you have any questions, please email them in.